So good morning, Happy New Year, and welcome back. Today we'll turn to the discussion of associated bundles. That's section 5.3. And an associated bundle is a bundle that's associated in a certain precise sense with a principal fiber bundle. So far we've discussed principal fiber bundles, and maybe it remained a little obscure how this relates to situations or to constructions in physics in particular, as you had them before. And in a sense, one needs to introduce the associated bundles in order to start grasping the importance of principal fiber bundles. So let's first start with the precise definition. Given a G principal bundle, and you remember that a principal bundle is first and foremost a bundle pi down to m, which as a bundle is isomorphic to p down p mod g, and that there is a right action of a Lie group G on the total space here. Okay, so given a G principal bundle, and so now you need something in addition, and a space, well, whatever it is, a smooth manifold, a topological manifold, let's say a smooth manifold, and the smooth manifold F on which there is, or on which we also have, a, now it is a left G action, and here we use this right G action on the total space of the principal bundle, but now we consider a left G action, so I use a symbol that looks very similar but points to the other direction. It's a totally different map. It takes a G and an element of this new smooth manifold F and takes it to F, and it is a left G action with the properties that this action had. We define the associated bundle, and so obviously whatever we're going to define will depend on the data given by the G principal bundle, by the choice of the smooth manifold F, and by the choice of the left G action written like this. We define the associated bundle, and this associated bundle has, of course, needs a bundle space, and that will be called P sub F, because it will be constructed from the F and the principal bundle. There will be a bundle map, which we also denote by pi f, just to show it's not the projection map here, and it goes down to the same base space. So the associated bundle will be a bundle over the same base space. Okay, so now I need to tell you what the pf is and the pi f by A. Now, in order to construct this pi f, we first need to introduce an equivalence relation. So let twiddle G be the relation that identifies the relation on P Cartesian product F. So first of all, we take the total space of the principal bundle and attach to each point of the total space this manifold F. But that's a very big manifold then. We'll make it smaller, again, by defining an equivalence relation and then only looking at the quotient space. But that means on P cross F, we established that any element of P cross F is supposed to be identified by this relation with an element P prime F prime, by definition, if and only if there exists a G in G. And now we got to be careful, such that P prime is P acted upon from the right by this G. Well, that's all we have. We have a right action on the big bundle space. And the F prime, however, be a left action, so that goes the other direction. It's another map, okay, acting on F, on an element in this manifold F. But now we require that it's the G inverse acting on that, okay? Then it's you can quickly see that this twiddle G is an equivalence relation. Okay, and it being an equivalence relation, we can thus consider the quotient space. And that quotient space, of course, P cross F, identified or modulo this equivalence relation. And this guy, instead of always writing this complicated guy, we write P sub F. Okay? Now, very roughly speaking, you know that well, not very roughly speaking, it's true. So the fibers of this P alone is the entire group. Okay? The fibers of because the P is a principal G bundle, and a principal G bundle has a typical fiber, the group. So very roughly speaking, what happens here, if you then mod out the group, what is left of this first factor? Well, essentially only the base manifold, very roughly speaking. And now you attach to it this fiber. So what we expect this to be is to be a fiber bundle. Well, we haven't written down the projection map yet, but we expect what we constructed here to be the total space, this PF, to be the total space of a bundle over M, where the typical fiber is F. But in this way here, by virtue of this action, it's tied to the principal bundle. Okay, fine. So anyway, we can consider this quotient space. And so obviously, so in other words, the elements of this PF are the equivalence classes P comma F, where P is any element in P and F is any element in F. So we will always think of this space here as these equivalence classes. And sometimes I'll even leave out these brackets because that lightens the notation. Okay? So anyway, that's this definition. And then B, we define the associated projection map that goes from PF down to M. Okay, we want such a guy. Now we can practice this for the first time. So we take an element of this associated bundle, which we understand as an equivalence class of a pair of elements from the principal bundle and the fiber, this being the identification under G, and we send this, by this map pi of F, we send it to the point in M that we get by pi of P. But now pi here, not pi down F, but pi is the projection we are handed from the principal bundle. Now you see here we take an equivalence class with a P and an F in there. Over here we just take one of the representatives. Well, not the entire representative because you need the F2, but part of it. And so we need to check well-definedness. Yeah? So this is well-defined since, okay, what do we need to check? We need to check that if we take any other representative instead of PF and apply the map pi f to it. So what is any other representative? Any other representative would have the form P acted upon from the right by some G, and G inverse acting from the left on F. This is clearly the same equivalence class as this guy. So I should say this is obviously the same as this by the very definition we made here for the equivalence. Okay, so now I apply the rule nevertheless. This is then by definition of pi f is pi of P acted upon from the right by G. And because this is the pi, the projection of a principal bundle, we recall that, well, what does this G do? It only moves us within the fiber. So this is the same as pi of P. But pi of P is pi f of P and F. Aha, so indeed the pi f, whether it acts on another representative or not, it produces the same result, and hence this map is well defined. Okay. Yeah, and so in total, the construction of this total space PF and the construction of this projection map pi f yields us a bundle. Now, I already gave you an intuition that if you mod out this G, that we expect a bundle, that this be a bundle over this base space with the typical fiber F. But strictly speaking, one has to show this from here, but that's simple enough to go to the problem sheet. So we have proof, namely the proof that the such defined pi f, pf by pi f to m is a, the restricted bundle, okay, yeah, is a fiber bundle with typical fiber, you know, that was the terminology, with typical fiber f, and that's going to be on the problem sheet. Okay. Now let's look at some examples. So let's start with the fiber bundle P, with which we start. Let's take the frame bundle. You remember Lm was the frame bundle that was at every point of the manifold. You look at a basis of the tangent space, and that, okay, so that's the, well, at all bases, that's then the fiber, that's the frame bundle. Okay. Now, we know, so we recall that if you have the fiber bundle, then of course you have your projection map of the fiber bundle and so on, and you have a right action. You have a right action of GL D, comma D comma R, and this D is the dimension of the manifold M, of the base space that underlies this frame bundle. You have such an action on the frame bundle, and it is given by acting on a frame, which we write E from the right by an element G of GLDR, and that this is then So if we write here the entire frame, so that's E1 to ED, and you act on this from the right by G, that this is afforded by the new frame E, and you have a G M1 EM GM2 EM dot 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 GMD EM. So as a physicist would say, you have a frame. Now you have a basis of the tangent space. You act on it with a GL transformation, a general linear transformation at every point. And of course, this is how the various basis vectors, frame vectors, transform. So we discussed this before, and back then in that lecture I told you you'll only grasp the full meaning or usefulness of this once we look at associated bundles. Well, that is what we're going to do now. Okay, so this is the principal bundle we started with, and now we let F in this example be simply the vector space, or the smooth manifold, the smooth manifold R to the D. Just the same D is the dimension of this M. This is going to be our fiber. So what we want to construct, we want to look now at an associated bundle over the base space M, which is the base space for this bundle, but with fiber RD. We already know such a bundle named the tangent bundle, right? But this is different because here I just tell you the fiber is RD. I have a principal bundle, which is the frame bundle. I also need to provide now an action of the same group, GLDR. So that's the, in this example, this is what the group in our general definition is. I now need to provide you also with an action, but a left action of G on there. So, so that's the first ingredient, that's the second ingredient, and the third ingredient is define a left action so that's this symbol that takes you from GLD, R and an element of F back to F, and we define this by F being acted on from the left by a GLDR transformation. The result will again lie in F, but F is an RD, so I can write down the eighth component, A running from 1 to D, and I define this as G inverse, the inverse GL transformation with components A, B acting on FB. So what we're going to model here intuitively is, of course, precisely what we do so often as physicists. We say, if we change the frame by this transformation, then we must change the components of an element in the tangent space. If this is going to be the tangent space, we have to transform the components like this. Now, when we looked at the tangent bundle, this was a conclusion from the definition of the tangent bundle that components must transform like this. Now, looking at the associated bundle point of view over the principal bundle, that's the frame bundle, we define it. We define the components to transform like this. Now you say, okay, seems a little bit complicated, but the point is, whenever you are allowed to define something, because that's an ingredient I can provide when constructing such an associated bundle, it means we could define it differently. Now, we probably wouldn't end up with the tangent bundle, but something else, but that's the point here. This reproduces something we already know, and next step we'll do something we don't know yet. Okay, so that's the idea here. We provide this as an input, and now we are done because I provided you with a principal bundle, with a fiber, and a definite left action, a specific left action of the same group that is are the fibers of the principal bundle on this F. So then L M sub RD pi down RD to M is the associated bundle. Okay, so the example ends after you provide the ingredients for the construction. Now, however, there is a claim. So once you have this, I have the following claim, that there is a bundle isomorphism that takes you from this thus constructed bundle, so Lm sub Rd pi Rd down to M. Now I have a bundle morphism. You know, a bundle morphism always consists of two maps. It consists of a map between the base manifolds, but there I use the identity, so it's a very special bundle map even. Bundle isomorphism M to the same base space that takes you from the such constructed associated bundle to the well-known tangent bundle over here, and that's the pi map of the tangent bundle. Okay, so this thing we just constructed. And this guy we know. And if I claim there is such a bundle isomorphism, I need to tell you by what map it is provided by. It's provided by the map U. And so we need to take an element of the associated bundle. You remember this guy here, LMRD, this associate bundle, this is simply the Cartesian product of the underlying principal bundle and the fiber we look at, but not all of this mod the identification with respect to this equivalence relation. Okay? And so the elements I need to take here are equivalence classes. And in this case, we take a frame, E, and an element of this fiber, F, and we send it to, well, this map sends this, takes an element from here, and sends this to F, A, E, A. And that's it, because that's an element of the tangent bundle. Okay? Because it certainly lies in some in some tangent space. So it's an element of the disjoint union of all the tangent spaces. Okay, so now if you then consider the action of this group on the fiber, you see that if you change the frame with the transformation G, then the fiber element, Fa, is changed in the opposite direction, and this just cancels. So this is an object that's invariant under the action of the group G as it is expressed by virtue of this equivalence class. And that's precisely what we mean as physicists if we say if you change the frame, you've got to change the component the opposite way. Okay, so this is why this looks like this. So this is all pretty trivial, and again, it wouldn't be worth the effort here because we anyway know how it works here. But here, again, the interpretation is the other way around. Here you don't conclude that the components transform like this. Here you impose that they do. Whenever you have this chance, you can do it differently. Okay, so that's the first example. Yeah, sure.
For isomorphism, the backwards maps, U inverse and it inverse?
Yes, that's right. That's right, and that you can check that that you can construct the map backwards, because if you have a vector in an element in the tangent space, you have such a guy. Now you could choose an arbitrary basis. Okay, good. Okay, thank you for the question. This is clearly invertible, since for any f for any x in Tm, that's not necessarily of this form at first, so for any x in M, we can choose. So for any x in Tm, there first of all is a certain base point, so this is x at P. We can choose a frame E such that x is Fa Ea, so that the f's are the components of this guy with respect to the chosen basis. And then you associate with x by virtue of what is it, U inverse, you associate with it the pair EF, namely of the chosen frame and the thus extracted components. Okay. Now you worry because you made a big choice. You made a choice of frame in order to decompose the vector into components. However, the choice of frame you have is a GLD transformation. This is invariant. So if I associate with x the pair EF, not the equivalence class, but the pair EF, this would depend on my choice of frame. However, I associated with it the equivalence class of the pair EF, and this definition of the equivalence class by virtue of this equivalence relation, I think it's still here on the blackboard, by virtue of this equivalence relation, exactly provides for all the other choices you could have made and identifies all these choices. That means this map is indeed independent. The result is independent of the choice of frame. Okay. This map is then independent of the choice of frame. And that provides the inverse map Julian was asking for. So in other words, what Julian was asking for is the question, why, from the point of view of the associated bundle, why can I choose an arbitrary basis in order to express my tangent vectors? This is the answer you're probably given in a less geometric course on tensors. A tensor is whatever transforms like a tensor, and the group it transforms under is the GL transformations, unless you restrict them. We'll come to that later. Anyway, and it is because we choose here the equivalence class. So this formalizes what is often said informally. And you see, let me comment some more. If you look at the definition of the associated bundle again, what is new here, if we think of, say, the tangent bundle as the associated bundle, what is new that all of a sudden when we're talking about, no, it's this blackboard, I'm sorry. So if we talk about the tangent bundle in terms of this associated bundle over the underlying GLD principal bundle. What is new is the involvement of this group, GLDR. You see, here, if we just look at the tangent bundle, there is no talk about any group at any point. Here there is. And so in physics, we sometimes say this is a GLD tensor, or this is an SO3 tensor. It's a tensor with respect to rotations. It's a tensor with respect to Lorentz transformations, and so on, or a vector. And all of a sudden, this group plays a big role. Now, so far, what we did is we only looked at, if we look at the tangent bundle, we looked at tensors, which physicists sometimes call GLD tensors, that transform under GLD. But what if you restrict the transformation? If you look at Lorentz transformations, you look at the transformations of tangent vectors, okay, to world lines, but you don't allow any general linear transformation, you restrict to only the Lorentz transformations, okay? If you think about the tangent bundle and you do this, you have to provide this somehow from the outside and saying, okay, look at this, but please only use Lorentz transformations, because for the special question we're looking at, we want to consider this. Well, if you want to make this precise, you go to here and you take the frame bundle and everything all right, but you then try to restrict, and we'll come to conditions under which circumstances this is possible, you try to restrict the group you're using in the underlying bundle. You restrict the group to whatever group you like, if it's possible at all. Okay? So that's one thing that's routinely done in special relativity, only looking at Lorentz transformations rather than general linear ones, but that only has its formally clear or precise place in this formulation of associated fiber bundles. So it's this involvement of this group. Okay? So that's another point where this is important. So the second example I'd like to look at is a straightforward extension of this. We again consider the frame bundle of some smooth manifold M as the principal bundle. We again take the group of this principal bundle as GL D, R, and we still have the right action we had before. Same right action of this GL on the LM as before. And now as the fiber, however, we take P copies of RD, so P copies of those, yet another Cartesian product with Q copies of the dual. Q copies of the dual. And it's really here, the star is now back there. We're of course going to write down an associated bundle to the same frame bundle, okay? But now we're writing down PQ tensors. Okay. Okay, so this is the fiber, and we define a left action of GLDR on this fiber by G acting on an element of F, and the result will lie in F, but F is a space of P copies of RD with Q copies of RD star. So we have indices I1 to IP, J1 to JQ, and that I write the indices up down. In this case, it's now again a new convention. Well, it's the old convention we always had, that we want vector components with indices up and covector components with indices down. Okay, but this is just a collection of numbers here at this point. So we have to, very strictly speaking, reintroduce the same convention again, because we're now dealing with these guys. Okay. And we define this as, and in order to make it simpler Well, it doesn't matter. I can just now take the f m. Ah, yes, yes. So this is the f I1 to IP, all indices twiddled, and J1 to JQ, all the indices twiddled, so they're different indices. And now every up index I transform by G I1 twiddle to IP twiddle, and then J1 twiddle up, J1 down, to JQ twiddle up, JQ without twiddle down. And here I have to choose the inverse G. Now you might be worried whether it shouldn't be the inverse G's here and the G's there. Well, but then if you do that, you have a G inverse here, which is actually the fashion in which we use it. So this is fine, because you do this for every G and GLD. Okay, so this is nevertheless, and that's my point here, again, that's the definition. You now construct a bundle of objects defined by components, if you wish, because this is just a Cartesian product, such that these components transform under the group G, which acts on the frame bundle the way we said before, but now these components transform like this. So of course you say, oh yes, that's the transformation law for the components of a PQ tensor. And of course we're recovering this way. Then LM sub, okay, now it's sub F for this F, pi Fm is isomorphic as a bundle to TPQM, to what before we called TPQM, which had a projection map that is the PQ tensor bundle. Okay, so that's now not a big surprise. This is just the extension of the previous example where we constructed the tangent bundle as an associated bundle to the frame bundle. Now we extend this to tensors. This is not very spectacular. Any question?
I'm a little bit confused with the lower indices of the G. Why are you running them from I? The first G, for instance, has got I1 on the top and I1 twiddle on the bottom, right?
Mm-hmm. Mm-hmm.
Wait. And then the second G has J1 twiddle on the bottom and
here.
IP on the top, right?
No. This is an I. IP twiddle, J1 twiddle, J1.
Oh, right, okay.
I'm sorry, so these are J's. So from here on, they're only J's, twiddled and untwiddled.
Okay.
And yeah.
Okay, yeah.
Okay? I think it looks right. So unless you, okay.
No, I'm sorry, I was just confused with the IP there. Just
Yeah.
a little bit like a J.
Yeah. Oh, I'm sorry. That's my handwriting. Okay. Fine. Good. Okay. So it's the PQ tensor bundle. So having done all this, we now provide the third example, and that one will be more interesting. So finally, but let me say one more thing to this construction. So again, in physics, we think about, say, you have some vector, you have some direction, and you say, let's rotate the system, right, by a certain, or rotate or transform to another frame by a certain amount. But so this is something that you do in the principal bundle. No? You choose a G, and then you can rotate the frame. And then if you understand the PQ tensor bundle also as an associated bundle to the same LM, as you before understood the tangent bundle as a specific associated bundle, the idea is that you rotate your frame and every associated bundle must follow suit. So you rotate a vector like this. That means at the same time you have to rotate all the tensors by the same transformation, right? And we could also think about the spinor bundle. If then we took here, for instance, C4 for the Dirac spinors or something like that. The only problem we then have that before we do that, we need to restrict this group here to a rotation group. Okay, that we can't do yet. But the idea is then you would also transform the spinors the same way. Okay, so it always depends on. So if we took the frame bundle here, but the SO13 frame bundle or SL2C frame bundle over space-time, you could then say, okay, if you rotate vectors this way, then you have to rotate spinors this other way, but this is always provided by the left action of the group you have, let's say SL2C for the spinors, for the relativistic spinors, how the group acts on the various associated bundles you defined. So there's this one principal bundle defining the frame, and if you do a transformation there, in all the associated bundles, things, the objects follow suit. Right? That's of course exactly the way we think about this stuff, right? Because otherwise, what is the point of changing, if you change the basis in your tangent space, who on earth instructs you to change the basis in your, say, PQ tensor space the same way? Because they're different spaces, you can choose bases as you like, right? So who tells you that you have to do this at the same time? Well, if you want to do this formally, if you want to impose this formally, you say, well, consider all these tensor spaces as the associated bundles, the respective associated bundles over the same frame bundle. Okay, that's the idea. So you see this ties together lots of stuff that we always say, do this at the same time. If this transforms like this transforms like that. Well, this is the formalization of this. Okay, but so all of this just reproduces stuff we already knew, but now comes the example C, and that amounts to a definition, of tensor densities. So again, LM, P is LM, G is GLD over R, and again, F is these components P copies of RD and Q copies of RD star. So the elements of the fiber look precisely like here. So if I write down an element of the fiber, it has this kind of shape. It's given by an array of numbers of this form. But now we modify something. But now we modify the action, the left action of the group on this fiber. Left action of the group GLD, group G, on F. Namely, G now acting on F must again, of course, produce an object I1 to IP, J1 to JQ, because that's what an action does. And at first it looks like it's the same, it's I1 as before, I1 to IP, J1 to JQ, and now we twiddle all the indices and write again G I1 twiddle to G IP twiddle, and then G inverse J1 twiddle J1 up to G inverse JQ twiddle JQ. So that's exactly what we wrote down before. If we left it like this, this would again be a bundle isomorphic to the PQ tensor bundle, but now we do something new. We write here in front another factor, namely determinant of the G. Of the G inverse. Let me think for a second. I think it's determinant of the G inverse to a power omega for some omega. And traditionally one would probably choose this to be an integer in Z, but some people now also consider them consider arbitrary numbers at least in Q or in R here, but let's stick to this for some omega in Z. Then, and now we cannot claim that this is isomorphic to some bundle we already know, because we don't know that bundle yet. Then, so we have to call this guy, then Lm sub this F pi F M, which only is distinguished from this bundle here, from this LMF pi F down to M, by the fact that the left action of the same group on the same fiber now picks up such a factor, is called the tensor density bundle. Over M, and the omega, we should call this the tensor omega density bundle over M. And the PQ tensor omega density bundle. Obviously, for omega to 0, this factor goes away, and we recover the tensor bundle. So a PQ tensor is a PQ zero density bundle. Another limit case is if these F's here, if there's just a real number here, one real number, it's a different fiber, but then the F is kept invariant and only scaled by this, we would call a scalar density. Okay, so maybe we write this down as the last example, because it formally doesn't exactly fall under this. So similarly, choosing F to be just R and the left action of GLD on F, so which is R, defined as G left on F is simply defined as the determinant of G inverse acting on F times F, but now F is just the one component in here. Okay, one obtains the scalar density bundle. Okay. So sections of this bundle would be scalar densities, a scalar density field. Sections of this bundle here would be PQ tensors, and sections of this bundle here are PQ tensor omega densities. Okay? Good. And I think I mentioned densities before with this determinant. I think we talked about this at some point, but this is the precise bundle theoretic way to think about densities. Okay? Good. And this you need. And you see the point about densities is that the determinant of G inverse isn't necessarily 1. Unless you restrict the group to a group where this is already given, that the determinant is 1. For instance, if you choose as the group not the general linear group, but you use the orthogonal transformations with respect to some metric, they have determinant 1, and then you don't see the tensor property. okay, which is one of the reasons why these tensor densities do not seem to appear, say, in special relativity, where we usually restrict the transformations to, say, the Lorentz group, which is an orthogonal group with respect to the Minkowski inner product. Then you don't see this stuff, but many objects that there you treat as a tensor are actually tensor densities, and only because the group is restricted, you don't pick up this determinant factor. Okay, so that's the whole thing. Yeah.
Are there any specific cases in physics where you do really see this?
Oh yes, definitely. You see this if you, we didn't do integrals yet, but if you want to integrate a function over a manifold, okay, and say the manifold carries a metric, you can only integrate over densities because your integral, so this is informally, yeah, so informally, we're going to do this more precisely. If you write down an integral d to the 4x, obviously you can only do this in a chart. You have already chosen a chart because in the manifold you don't, so you do this. And now if you just take a function f of x1 to xd, also with respect to this chart, and you want to define by this, you could say, well, so you do this over, So let's assume the whole manifold is covered by one chart. If it's not, we have to do a partition of unity and so on. But let's assume the whole manifold is covered by one chart, and you want to calculate the integral of a given function over the entire manifold. So you want to define something like integral over the entire manifold of a function f. Let's assume we want to do this, okay? So that's something you want to write. This d for x is just, this is already in the chart, okay? So you push this down to a chart, there you can do this. But now assume you had chosen a different chart. You know what happens then? If you choose a different chart, you pick up by the rules of integration in the chart, which is analysis on RD, you pick up a Jacobi determinant of the new chart map with respect to the old one, right? Now that's of course a disaster. Well, you would then replace this by another function here, but that's in a sense a disaster, not in a sense, it's a disaster because this changes the value here. So what you need to do, you need to cancel this guy. So what you actually want, but this here is the transformation of chart, so this is the G here, and if now this f is not a function, but it's a function density, so it picks up what we wrote before, picks up just this determinant factor. This, under the same transformation of chart, will pick up this guy. That's because there's the G inverse, and those will cancel. And the result is, so I put a twiddle on top in order to indicate a density. You cannot integrate a function, you can only integrate a function density. So this is the informal bit. If you want to make it very clear, what you have to do here, you have to integrate over forms. And you use a volume form, which is automatically a density and so on. So we're going to do this later, but the point is you very often want to look at density. So you probably also in field theory talk about the Lagrangian density. No? The Lagrangian density is indeed a density. Okay, it's not a scalar, it's a density. Because you integrate over it, but then, okay, so you got to be careful there. Okay, so this appears everywhere, certainly everywhere, where you integrate over a manifold, push it to a chart, but in order to have something well defined, you need to understand densities. It's also, and that's the same thing if you think of general relativity. I don't know whether you attended that lecture, but if you write down the Einstein action, you write here that G, something like this, times the Ricci scalar. And the point is that this det G is a 2 density, because you can check how the G transforms as a tensor, and you have the determinant of it, and you have det of, now let's assume, okay, this G is now misleading. So here the G was the G of the group. Let's write a capital G for the space-time metric. Now you can check how the space-time metric transforms under transformations of the general linear group. So these transformations are now given by GAM GBN. We know that it does it like this because this is a tensor, but now you can use the rule for determinants. You find this determinant GAB times the determinant of this G, but you had two of those, so it's this squared. So you pick up a squared factor here. So this is a density of weight 2. This omega is called the weight of the density. Densities of weight 2. Okay, so this appears everywhere where you integrate over manifolds and you push it to a chart. Okay? But again, the very precise definition of integrals requires us to integrate over forms. Let me briefly clear up some confusion. There was a question in the break. We defined the left action of G on a fiber, say in the context of example A. No? So this is add example A. And I said, well, because the fiber is RD, we define this as G inverse AB FB. Well, if you really want to get this together with what I said before, at this point, I think you need to remove the G inverse, because you remember that here the equivalence classes PF, they were defined such that the right action of the G, so not this left action, but the right action of G on the principal bundle, together with the left action of G on the fiber, but there we already put the G inverse, that this actually needs to, if you send this via this map, don't remember how I called it, U maybe, if you send it via this map U to so let's do it here, by U to F BEB, which in this special example, the principal bundle was given by the frames, okay, such that this is an element of the tangent bundle in a well-defined way, but obviously with our definitions before, we need G inverse here in order to then have a G inverse BM FM, and here a G N B En, and that only works if this G inverse here goes against this one, but in order to have this, because we put the extra inverse here, you have to lack the inverse there. Okay, so that was a confusion, and in the other examples I provided, I think I did it the right way. But anyway, the ultimate check is whether these transformations cancel such that if you use this map, you get back an element of, in this case, the tangent space, the tangent bundle. Okay? All right. So now what did we do? We defined a new construction for bundles starting from a principal bundle, choosing a fiber and a left action of the principal bundle group on that fiber. And that is, we saw that from this we construct a bundle, a fiber bundle with fiber F. Now we discussed bundles before, but these associated bundles are special bundles because they can be constructed from a principal bundle. So there is more structure to these associated fiber bundles than there is to fiber bundles. Okay? So also the tangent bundle, considered as an associated bundle to the frame bundle, that was our example, is a bundle that has more structure because the structure group is in there. And whenever we have more structure and we look at structure preserving maps, as we always do for all our objects, we need to take this structure into account. So therefore, we'll now define, again, bundle maps, but now maps between associated bundle. And these will be called associated bundle maps. So an associated bundle map, rather than just a bundle map, an associated bundle map between two associated bundles which share or sharing the same fiber. sharing the same fiber, but being associated to arbitrarily different respective principal bundles to arbitrarily different respective G principal bundles. So both principal bundles also share the same group. An associated bundle map U twiddle F twiddle. Now let's call it H twiddle. We always U twiddle H twiddle. So let's write down. So we have principal bundles P and P prime. So how does that work? We have a P sub F is the associated bundle to this first principal bundle down to a base manifold M. And we have another P prime F, which however projects down to another M prime, because this P prime principal bundle may have a different base space. And then the bundle map U twiddle H twiddle sits here. An associated bundle map between two associated bundles. Is a bundle map. Is a bundle map. So no talk about associated bundle map. Is a bundle map which can be constructed from a principal bundle map between the underlying principal bundles. So let's write down such a map between the underlying principal bundles. So we have the principal bundle P down to M, that's the projection pi. We have another principal bundle P prime, where with the projection pi prime we go down to M prime. These are the two principal bundles. But we also want the right action of G on this guy, and we want the right action primed of the same group G on this guy, so we arrive at P and P prime here. Okay? And so we say it can be constructed from a principal bundle map, and let's call this principal bundle map U and H. And you know that that's a pair of maps, Q and H. Okay? And then, of course, this U appears up here again. From principal bundle maps. And let's recall quickly what a principal bundle map was. A principal bundle map is a bundle map. That means it respects this part of the diagram to commute. That means from here we get pi prime after U is H after pi. Okay, that we get from here. And that would be a bundle map. This principal bundle map, it becomes a principal bundle map by only also respecting this up here to commute. That means by U of P acted upon from the right by the unprimed right action with a G, that this is the same as first mapping the G with a P and then using the primed right action of G. Okay, for all P in P and for all G in G. Okay, so again, where are we? The sentence isn't finished yet. So an associated bundle map is a bundle map. Well, these are two bundles. UH is a bundle map. Okay, so certainly also here we already at this stage can require that you twiddle. Okay, here we need still pi f and pi primed f. That you twiddle, no, that pi primed f after you twiddle must be h twiddle after pi f. Okay, so an associate bundle map is just a bundle map, which, however, can be constructed in a specific way from a principal bundle map, which is this. As, and now I tell you how it needs to be constructed, as u twiddle u twiddle needs to eat an element in PF in the associated bundle. How does it do that? It takes an element in P and an element in F, but we take the equivalence relation so that the result lies in PF. And we need to be able to construct this U twiddle, if it is to be an associated bundle map, as U of P comma F, and then the equivalence bracket. So we use this U to take the P element to an element in P prime, and then this is the equivalence relation that defines this guy here. We lie over there. Full stop. So now the sentence has ended. The principal associate bundle map is a bundle map with the additional property that it has to be induced from some principal bundle map in this fashion. And we also got to provide the H prime of P and F, and that is supposed to be the H. That's the H down here of pi of P. And then this U twiddle, H twiddle has to take this shape. It's induced from here. Okay? And obviously, by virtue of requiring that this UH is a principal bundle map, we take into account the very specific structure of an associated bundle. Okay? So the two remarks. Yep.
Why H twiddle eats a P comma F and not element of M, or is
You're right. You're right. You're right. This should eat an element. That is right. I'm sorry. That was nonsense. Well, if it does this at all, it would first project, but of course nobody wants this. So it eats an M and maps it. It maps it the same way. This is the same thing down here. Thank you very much. That's right. That's right. Okay, so I should say for all P in P, F in F, and M in M. Another question? Good. So remarks. Two fiber bundles, two F fiber bundles may be well, let's say maybe isomorphic as bundles, which means, recall, this means there exists a bundle isomorphism between them. But may at the same time fail to be isomorphic, fail to be isomorphic as associated bundles. Which means there exists an associated bundle isomorphism between them. And that's the whole point of the previous definition. There are fiber bundles, these associated bundles. They're F fiber bundles, but two fiber bundles that as bundles are the same are not necessarily the same as associated fiber bundles. Okay? Because there's more structure. So if this wasn't the case, then the definition would be vacuous. We could always use the fiber bundle definition for isomorphism or for a bundle map. But because this is the case, it really shows that there is more structure in in a fiber bundle that arises as an associated bundle. This carries more structure than a plain fiber bundle. So that's remark 1. Remark 2. When discussing fiber bundles, you remember we had this definition of a trivial fiber bundle, and that is if there exists a bundle morphism. Oh, well, let's write it down. Recall that a fiber bundle, an F fiber bundle, was called trivial if there existed a bundle isomorphism that takes your fiber bundle with total space E, projection map pi, and obviously there is a fiber F. If there was a bundle map U, let's call U twiddle H twiddle, to M cross F, and this was the projection to the first factor. Remember this? But this needed to be a bundle map, and then we called this bundle trivial. That was it, okay? And then we had that a principal G bundle was called trivial, so fiber bundle, a principal G bundle was called trivial if there was a principal bundle map. There was a principal bundle map that took us from here to here with the U, and then to P mod G, where we modded out this group. If there was a principal bundle map of this type, and remember that the whole point of the principal bundle map was, had it several times, that there's a certain right action here, and you also require not only that this be a bundle map here, but also that there's this compatibility condition up here. We just wrote it down before. So it's a stronger criterion. And but now here, an associated bundle is called trivial. Now it's not so convenient to define this again by a similar structure thing here. We simply say it's called trivial if the underlying is trivial, if the underlying principal bundle is trivial. That's the definition. And then we can have it as a theorem that a trivial associated bundle, a trivial associated bundle is a trivial fiber bundle. Okay. Now that sounds funny because an associated bundle is a fiber bundle, is a particular instance of a fiber bundle. So if you read this, a trivial associated bundle is a trivial fiber bundle, it seems almost like a tautology. Well, it isn't, because if we say trivial associated bundle, we mean the underlying principal bundle is trivial. And if I then talk of it as a fiber bundle, I would look at the associated associate bundle, which is a fiber bundle, and I can then show that this associated bundle is isomorphic to its base space times the fiber M. Okay, it's a non-trivial statement. Trivial associated bundle is a trivial fiber bundle, but the converse does not hold. The converse does generally not hold. Well, it couldn't be decided, because if you have a trivial fiber bundle, how do you know it's what associated bundle it is? Anyway, even if you knew this, it will not necessarily be that the underlying principal bundle is trivial, even if as a fiber bundle the associated bundle is trivial. Okay, and here the proof, an instruction to the proof will be on the problem sheet. Okay. So this is a kind of warning. Whenever you are handed a bundle and somebody claims it's trivial, you're going to ask, hang on, is this just a bundle? Is it a principal bundle? Well, then you will probably already know. Or is this or do we consider this a specific associated bundle? In each of these three cases, triviality has another meaning. Okay, so it's important to remember this. This is the usual business of refining the maps between objects according to the structure they carry. So now we come to an important theorem which again should clarify a lot, and that's the following. So let me call this important theorem. At least it will be practically important, and it will clarify what precisely is the difference between a section on some bundle and a function on some bundle. And it works only for associated bundles, but as we saw, that's the case we're interested in very often. Important theorem. The sections sigma from M to Pf of an associated bundle Pf pi Fm are in one-to-one correspondence, to, and now it comes. But whatever comes, it will be a precisely equivalent idea of thinking about sections of an associated bundle. For instance, if we talk about sections of the tangent bundle, we know these are the vector fields, sections of the tangent bundle. We will now, if we consider the tangent bundle as an associated bundle, we add some more structure and think about how the frames transform, then we will now be able to think of vector fields in yet another way. Okay, for instance, so the sections of an associated bundle are in one-to-one correspondence to, now it comes, to f-valued functions. Aha, interesting. So we always said that sections are not functions. They're locally, if the bundle is locally trivial, you may be able to write it locally as a function, but globally it's not a function, a section. A section is a section. Okay? But now we'll be able, if we have an associated bundle, we'll be able to understand a section on such an F-fiber bundle as F-valued functions on, well, you might guess it, on the underlying principal bundle. Functions, tralala, on the underlying principal bundle. So what does this mean? If we think of a vector field, we cannot necessarily think of it as a vector-valued function on the manifold. I mean, that's what our intuition is. At every point of the manifold, there is a vector. But a vector-valued function, that seems to be exactly this, but it isn't, because the section is not that. But if we then go to the principal bundle, and we attach to every point of the principal bundle an f, a vector, such a function directly translates to a function on the associated bundle. Okay? So that's kind of interesting, because you can always think of a section as a function, but only on the underlying principal bundle. Okay? And the section is then given as, so if you have this phi, so proof, I also put this on the problem sheet, but I give you some hint already. Proof on the problem sheet. And the key idea, and the other key ideas you can guess from there, the key idea is that the section, so given a phi, so if you want to show this way, and it's an if and only if, or it's one-to-one, so you construct this, given the phi from P to F, construct the section S sub phi, because it's induced from this phi, then a section from M to Pf, at a point x in M. Define this as, now we need a point in Pf, and that will consist of P phi of P, because phi yields an element in the fiber here, and you need to say what F is, what P is, where P is any element in pi inverse of x. And of course you have to show that this is well defined, simple, and invertible. The invertibility you need in order to ensure that it's one-to-one, of course. And here you show the invertibility by explicitly constructing the inverse. Okay? Anyway, but that's this theorem, and that's very important, and it's so important that I think it's worth doing the proof yourself, because then you really will recollect the theorem in the future. And on the problem sheet, I'll also provide examples for this, applications for this. So then the final definition and theorem I want to provide for associated bundles is the following, is the restriction and extension of bundles. So definition. Let H be a closed subgroup of the Lie group G. So now we're going to deal with associated bundles with respect to different underlying principal bundles. Well, first of all, we'll talk about different principal bundles. So let H be a closed subgroup of G. And P a G principal bundle and P prime an H principal bundle. So two principal bundles with different with respect to different Lie groups, but both over the same base space. Now, if there exists, well, could we talk about a principal bundle map between these two principal bundles? No, because a principal bundle map we only defined before for two bundles with the same Lie group, or between two principal bundles where you have different Lie groups but where you're additionally given a group homomorphism from one into the other. That's not the case here. Here we're given two Lie groups and one is the closed subgroup of the other, but a subgroup can lie in the other group in various ways, and unless you specify how by a group homomorphism, you don't know how. So with the definition so far, if I now continued writing, if there exists a bundle, a principal bundle morphism, you would say we don't have enough data to write this down. And you'd be right. And that's not what we're going to do. It's going to be the definition. If there exists a bundle map, not principal bundle map, but bundle map, let's write it down, P pi m, one bundle, P prime, pi prime, the same m, however. Now here we have a right action of the G. Here we have the right action of an H, of which is not related to the G by some group morphism. We just know it is a closed subgroup of G, P prime. If there exists a bundle map UH, and bundle map, as opposed to principal bundle map, only means pi prime after U is H after pi. It's only this down here, but there is no, I cannot even write down any condition here because I don't know how one maps to the other. If there exists a bundle map, but now we need to write down a condition, so I couldn't, you see, if I wrote principal bundle map, I should have written U for any P on which a G acted should be U of P upon which from the right, or now I need an element in H, but all I have is an element in G. If I had a bundle group homomorphism from G to H, I would use rho of G, if rho takes me from G to H or something like this. But I don't have that. And all I can do, but I know that the H is a subgroup, a closed subgroup, and in particular a subgroup. So I can play the game if I restrict here to H, and then I only use the H here, and that should be a primed action. Then I use an H here, and I require this not for all G, but only for all the H in the subgroup. Of course, for all P in P. Okay? So in a sense, this is a weakening, an appropriate weakening of the idea of a bundle, of a principal bundle map, by requiring this only for the subgroup, that this bundle, this principal condition holds. Okay? If there exists a bundle map, then, okay, I need, fortunately it's too big.
Sorry,
yeah.
Just a notation thing, that the H from M to M should be a different H than the H on the right side.
Yeah, exactly. So here we can then again write an F here. If there exists a bundle map UF. I just, that's right. I just, before I switched to H because the F was used for the fiber. Now I have got the opposite problem, so I revert to F here. Okay, right. if there exists such a bundle map, okay, I moved the blackboard a little bit and continue here, then, come on, okay, then P pi m is called a G extension of the H principal bundle P prime pi prime m, and at the same time, well, no, a principal bundle and P prime pi prime m is called an H restriction of the G principal bundle P pi m. Okay, so if one is the restriction, the other one is the extension. That's the idea. Okay? So we can only make restrictions to closed subgroups, or we can make extensions from closed subgroups if there exists such a bundle map with that property. And the question is, when does it exist? But before we look at this question, let's think about what we're looking at here. There are different groups, and example, we might want to look at something like this. We might want to look at SOD as a closed subgroup. So H chosen as SOD as a closed subgroup of G of GLDR. So we might want to, for instance, study principal bundles where the transformations are only rotations and want to see whether there is a restriction of the original bundle that gets you there. So from the frame bundle with this group to the frame bundle with respect to that group. Okay? And the question is whether this exists. Maybe it is not always possible for any base space and so on to restrict GLDR to SOD. In fact, it is. And if one thinks carefully about it, which now we don't have the time and I'll think to maybe put this on the problem sheet, the possibility to restrict GLDR to SOD amounts to the question, can I equip a smooth manifold where you know nothing, where you have GLDR, can you equip a smooth manifold with a Riemannian metric? It turns out this can always be done. Okay? You could also ask the question, what about choosing the smaller group SO1D, which is certainly a subgroup of, it's also a closed subgroup of G chosen as GLDR. So can you restrict to, say, the Lorentz group? And it turns out, no, not always. There are certain obstructions that can appear. So not every manifold can be equipped, every smooth manifold can be equipped with the Lorentz metric, but everyone can be equipped with the Riemannian metric. Okay, yeah? Yes, but I also went one dimension up. Okay, thank you. That's right. Yeah, that's right, because of here. Yeah, you're right. That was inconsistent. Thank you. Okay. Okay, so that's the questions there. And, well, theorem. Well, that's a rather simple theorem, but it's good to know. Any H principal bundle can be extended to a G principal bundle. so extended to a G principal bundle, well, if H is a closed subgroup of G. Well, that is, of course, part of the definition, but we emphasize it again. Okay. So you can always make the group bigger. Bigger if it's in such a way that the group you had before then is a closed subgroup of the bigger group. So very roughly speaking, extensions are always possible. There's no constraint on how you can extend. But now there is the theorem on restrictions, and that is a G principal bundle P pi m can be restricted to an H principal bundle if, well, the first condition is again obvious from the construction before, if H is a closed subgroup of G. Okay, fine, that's not the key thing. It's like here, no? So you can again put this in brackets. That goes without saying, but it's meaningful to emphasize it. If the quotient bundle, that's the main condition, P mod H to M, where you here use the canonical, well, there is another projection map pi prime, which however you can easily construct by going from P to P by H by the canonical isomorphism for the respective equivalence relation. If this bundle has a cross section, you remember we already before had this theorem that says a principal bundle is trivial if it has a cross section, if and only if it has a cross section. Remember that? A trivial bundle is trivial. A principal bundle is trivial if and only if it has a cross section. Now here, from this G principal bundle, we consider this quotient bundle, and if and only if, that's if and only if, that's the interesting thing, if and only if this quotient bundle has a cross section. And so examples, well, the two before. No? So if I take here the examples 1 and 2, LM, so that's again examples 1 and 2 from before, LM mod SO3 2M always has a cross section, and 2 LM mod SO1 comma D minus 1 to M may or may not have a cross section. So for instance, if M is the sphere, is the true sphere, then LS2 mod SO1 comma 1, which is a subgroup of GL2, which is the, of course, in this corresponding frame bundle, the respective group. SO1 comma 1 does not have a cross section, or in other words, one cannot establish or equip the sphere S2 with a Lorentzian metric. What does this have to do with the Lorentzian metric? Well, if you take the frame bundle, if you take a manifold and you equip it with a Lorentzian metric, you can construct an orthogonal frame bundle from that. So, so for a smooth manifold M for which you have a Lorentzian metric, you can construct from it an orthogonal frame bundle, okay? And then this works always. But for some manifolds, this cannot work, and that cannot then be associated with a Lorentzian metric, okay? So, so maybe here the conclusion is a little bit mysterious, but these statements here can be proven. It's not so simple to study the obstructions here. So these examples are not easily checked, okay? But nevertheless, they are facts, and this is the key. This is the key theorem that tells you whether or not you can restrict the group. And given how often we do this in special relativity and maybe general relativity in order to establish spinors where we choose SL2C instead of SO13 and so on in 4 dimensions, this is an important theorem. And there are again manifolds that can carry a Lorentzian metric, but still LM by SL2C doesn't have a cross-section. That means these manifolds are Lorentzian manifolds, but they cannot carry spinors. So not every smooth manifold can carry a Lorentzian metric, but not any Lorentzian manifold, even if you have made that hurdle, can then carry spinors. And these are important questions of whether a manifold has a spin structure or not, and it therefore admits the definition of fermions or not.